Hello students, myself Ishwaran Gujar, Assistant Professor, Department of Physics, IDSC Government College, Chikmagaluru. Today I am going to explain Biprism, Lloyd's mirror, comparison of interference pattern with prism, classification of interference. The phenomena of interference usually produced by two ways. First one, division of wavefront. Second one, division of amplitude. Next, we will move on to the division of wavefront. So in this case, the incident wavefront is divided in two parts by using the phenomena of reflection, refraction, or diffraction. These two parts of same wavelength travel some different optical path and superpose over each other to produce an interference pattern. In this device, a point source or the line source is employed. Example, Fresnel biprism and Lloyd's mirror. Second one, the division of amplitude. So here we use a thin transparent film ABCD of refractive index n to get the division of amplitude. The light from the source A fall on the upper surface of the film AB. Part of the light is reflected, part of the light is get refracted. Again, these refracted light fall at this point. A part of the light is get reflected and part of the light is get refracted. So this process is continue until the intensity of light become zero. So here the amplitude of incoming beam is divided in two parts either by parallel reflection or the refraction. These divided part superpose after traversing a different path and produce an interference pattern. In this device, a broad light source is employed. Example, Newton's ring, Michelson interferometer. Next, we will move on to a biprism. Biprism is an optical device that is used to obtain coherent source from a single source by refraction. Name itself suggests that biprism it consists of two acute angled thin prisms with their bases in contact with each other so as to form a single prism of obtuse angle of about 179 degree. So here the light from the sources is fall on the prism. So after refraction it is emerging along this direction. When this emergent ray produced in the backward direction, it meet at the point S1. In the same way, another ray is incident on the prism. After refraction, it emerges along this direction. If you produce this emergent ray in the backward direction, it meet at the point S2. So these two rays is appear to coming from the source S1 and S2. So here S1 and S2 are two virtual sources originate from the source S. So here the S1 and S2 act as a coherent sources. Next, we will move on to the production of fringes in a biprism. The experimental arrangement consists of slit S, the biprism A, B, C, and microscope M. All are mounted on an optical bench. These are adjusted at the same height and can move and rotate as required. The light emerging from the slit S fall on the biprism. The edge A of the biprism divide the incident wavefront into two parts. One is through upper half of the prism and other the lower half of the prism. when the light from the source S fall on the upper half of the prism, it bend in the downward direction. In the same way, when the light from the source S fall on the lower half of the biprism, it is bent in the upward direction. When we proceed these two light rays in the backward direction, it meets at the point S2. In the same way, when we proceed these two light rays in the backward direction, it meets at the point S1. And these rays is appear to coming from the source S1 and S2. So here S1 and S2 is act as a coherent sources and it originates from the single source S. So that the light rays from the source S1 and S2 are superposed over each other and it produces an interference pattern on the screen. Next, we will move on to the determination of wavelength of light. The wavelength, the lambda of light can be determined by following formula. That is, lambda is equal to beta d by d, where beta is the fringe width, the d distance between two virtual sources, the d is distance between slit and eyepiece where fringes are absorbed. To determine the wavelength of light, the following measurements are made. We know that the lambda is equal to beta d by d. By knowing the value of fringe width, distance between two coherent sources, and the capital letter D, we can determine the wavelength of light. First one, the measurement of fringe width. We know that from the definition of fringe width, the fringe width is nothing but the distance between two consecutive bright or two consecutive dark. To get beta, fringes are first observed in the field of view of microscope. The cross wire is made to coincide with one of the bright fringe and the reading on the microscope is noted. Then the micrometer is moved such that the cross wire coincide with second, fourth and sixth fringes and the readings are noted. The mean width of a definite number of fringes is calculated, from which the fringe width beta is determined and is given by beta is equal to distance moved by the number of fringes passed. Next, the measurement of D. The distance between the source and eyepiece is directly measured on the optical bench. Next, we'll move on to the measurement of the distance between the two coherent sources. The value D is the distance between the two virtual sources S1 and S2. We cannot see the two virtual images, then how can we find the distance between the two images? So that's why here we use the conjugate foci method. So in this method, we can use biconvex lens. The image formed by the lens is magnified and diminished. We can shift the position of lens to get magnified and diminished image. So first we place the convex lens at the position L1, then here we can get the enlarged image. We know that from the definition of magnification, magnification is equal to height of the image by height of the object. Therefore, in the position L1, the d1 by d is equal to v by u, where v is the image distance and u is the object distance. Now we can change the position of convex lens to L2 When we shift the lens L1 to L2, we can get a diminished image. So in the diminished position, that is in the position L2, D2 by D is equal to V1 dash by U1 dash. So here the image distance is become object distance and object distance is become the image distance. Therefore, D2 by D is equal to U by V. When we multiply the two equation, the d1d into d2 by d is equal to v by u into u by v. So here v u will get cancelled. So here then the d1 d2 is equal to d square, or d square is equal to d1 d2, or d is equal to root of d1 d2. By knowing the value of d1 d2, the distance between the two virtual sources can be determined. By substituting the value of beta, d and small letter d, we can determine the wavelength of light. Next, we will move on to Lloyd's mirror. Lloyds, in the year 1834, performed an experiment on the basis of division of wavefront. The arrangement for producing an interference pattern with a single light source is known as a Lloyd's mirror. The experimental arrangement consists of plane mirror MN and slit S1 is illuminated by a monochromatic light placed in front of the mirror. Here the light ray from S1 is fall on the plane mirror and the reflected ray reach at the point P. The another ray is incident on the plane mirror and get reflected and reach at the point Q. These two reflected rays produced in the backward direction, it meet at the point S2. Here S1 produce a virtual image S2 and thus they form a coherent sources satisfy the condition of interference. The direct ray S1P and S1Q from the slit S1 and the reflected ray MP and NQ, which is appear to coming from the source S2, are superposed and produces an interference pattern on the screen. Let us draw a perpendicular from the midpoint of the line S1, S2 on the screen where intersection point is O. Thus, in Lloyd's experiment, less than half of the interference pattern is available. In Lloyd's experiment, the reflected beam from S2 have suffered reflection at a denser medium undergoes phase change of 180 degrees, while the direct beam from S1 does not undergo such phase change. So that's why in Lloyd's experiment, here we can get a central dark band. So let 2D is the distance between the two coherent sources S1 and S2. Lambda is the wavelength of light used. D is the distance between the line of source and screen. Then we know that the fringe width is given by the equation beta is equal to d lambda by 2d, and the wavelength of the light is given by lambda is equal to beta 2d by d. By knowing the value of fringe width, the d, that is the distance between the two coherent sources, and the capital letter D, we can determine the wavelength of the given light. Thank you.